So chapter 2, this second week of school, and the topic that we're going to go over today is plate tectonics. So remember Alfred Wegener, 1915, so I want you to know this for the quiz. In 1915, Alfred Wegener proposed a hypothesis. He called that hypothesis continental drift. He had proposed that the continents, the current continents that we see today, at one time had formed a supercontinent that he called Pangaea. His lines of evidence were the fit of those continents, matching fossils, matching geology across the continents, and paleoclimates. We're going to go into those today. Today we call his theory, which was initially rejected, plate tectonics, because we discovered three amazing things throughout the last 100 years of research. One, we discovered the Earth consists of plates, and that these plates are moving. Second thing that was discovered was a process called Paleomagnetism. I'll explain what exactly Paleomagnetism is. And seafloor spreading, that the Atlantic Ocean today is actually growing larger. It grows every year by about that much. Not a whole lot that we can see from year to year, but over a span of geologic time, 250 million years, the Atlantic Ocean has literally opened up from its once position where there was no Atlantic Ocean, when Africa, South America, North America, Europe, Eurasia was all together in one big supercontinent. A ridge basically occurred between these continents that we have today. That ridge opened up. It deposited very black, very dark, iron-rich volcanic rock that when it cooled, it formed depressions, low spots, because it is dense rock. It's very heavy rock because of the iron content. As it turns out, these depressions, these low spots that will form throughout the Earth, became oceans, because water is going to flow into the lowest spot. That's why the Atlantic Ocean is there today. Out in the Pacific Ocean, we have the same thing. We have basically a seafloor that consists of basaltic rock. Basaltic rock is more dense, it's heavy, it sinks, and then water will occupy the lower parts of the Earth's planet. Topographically, water likes lower spots. So plate tectonics, the scientific revolution begins. So if we look at our Earth in comparison to the rest of the solar system, Earth is the third planet. Right now there are telescopes that are being launched out into space, and the primary focus of those observation instruments are to look for the third rock from the sun. And they've identified a lot of stars that have planets that are similar to our solar system, and they're looking at the planet that's close enough to the sun to receive adequate heat and sunlight. The ones that are further away don't receive enough solar radiation, and they're cold, like Pluto is a big ball of ice basically. As it turns out, the planets that are closer to the sun, because of their gravitational pull, those planets tend to be rocks. So Mercury is a rock, Venus is a rock planet, Earth is a rock planet, Mars is a rock planet. When you start getting these larger planets, the major component of these planets are gases. They might have solid components in the center parts of the planets. We haven't been there to explore them yet, but for a large part, Jupiter, Saturn are huge bodies of gases. So our planet is very unique when we look at the rest of the solar system. When it all began, one theory is a Big Bang, a supernova. Everything explodes, and today the universe is expanding. So that explosion that occurred that hurled everything out into space is today expanding. Earth, in comparison to some of the other planets like Jupiter and Saturn, is relatively small. It's a small planet in comparison, but yet we're just the right size. We have active plate tectonics. We have an atmosphere that can sustain life as we know it. And so Earth is very unique. So, like I said, if you look at the planets, you look at our solar system, here's the sun. We're in that position where we receive an adequate amount of solar radiation. And luckily, the Earth has a shield around it. In fact, it's like a force field. It's an electromagnetic shield. And that electromagnetic shield basically protects the Earth from harmful solar radiation. Earth is very similar to Mars. It's a rock. It's very dissimilar to a lot of planets. So Mars currently, the current state of Mars is about where Earth was about 3.2 billion years ago. Our Earth, as we know today, is about 4.6 billion years old. That's basically the consensus of most scientists. We'll get into radioactive dating and ages of things later on. Interesting thing about solar systems and the universe in general is that we have recognized that there are certain orbital belts that contain essential elements. And Earth has the 16 essential elements that are required to sustain life. Things like nitrogen, oxygen, hydrogen, ammonia. Those things are really essential for life. And water, of course. And one of the theories is that as the universe expanded and these bodies went from a point of origin in the center and went outward, that they encountered these various bodies, these various zones, and that those planets captured essential elements and compounds to make the components of those planets that they are. And for us, we have the right combination, the right temperature in order to sustain life. If it wasn't for the atmosphere, this is what the Earth would look like. In fact, this is what the Earth looked like in its early formations. The Earth went through 3 different processes. There were 3 different phases of Earth's development. We're on the 6th phase right now. There probably will be a 7th. In historical geology, we go into those 6 phases of the Earth's development. And so the Earth is unique because of these 4 following physical aspects. 1, the Earth has an iron core in the center. Now some people hypothesize that that iron core is solid. Other physicists say it's more liquid or more like silly putty or Play-Doh. That it's kind of like not a liquid but not a solid but very flexible. They think it has more of a solid consistency because of the pressure as the Earth spins is putting pressure on that center part. Even though it doesn't make sense that it would be a solid because of the temperature of the center of the Earth, but because of pressure can actually substitute for temperature to make something solid. So the Earth has an iron core. And because it has an iron core, this helps create what's called the electromagnetic field, the EMF. Surrounding the core is magma, and that magma is circulating in a process we call convection. If you put a pan of water on a stove, turn on the heat, the gas, the electric, as that element, the heat element or the gas flame, heats that bottom part of that water in that pan, that hot part of that water is going to rise to the surface. The cooler water at the surface of the pan, at the top, is going to sink and go to the bottom. So you get this circulation, convection. This is what magma does underneath our feet right now. And this magma is rich in iron. So as this iron-rich magma circulates around the iron core, it creates an electromagnetic field. This electromagnetic field is what holds in the atmosphere. The atmosphere burns up most of the space objects, asteroids, those small little rocks that come to the Earth, like all the other planets, and it basically burns them up in the atmosphere. What's nice about the electromagnetic field, it holds in the atmosphere, it retains the heat, so we need heat, and it retains the essential gases. It protects the Earth from very harmful solar radiation. The third thing that makes the Earth unique is an atmosphere. So you just can't say atmosphere. You have to say atmosphere because Venus has an atmosphere. Not very good for life. We couldn't survive there. Mars has an atmosphere. It's just void of oxygen. Lots of CO2 there. Wouldn't be a good place for us to live. Trees could possibly live there. So electromagnetic field holds in the atmosphere. The atmosphere, it consists of oxygen. The greatest component of the atmosphere is nitrogen. Nitrogen is very important in biological processes. Trees need nitrogen. Plants need nitrogen. Greenhouse gases. So these are greenhouse gases like carbon dioxide, CO2. Methane, which is CH4. Those greenhouse gases, and of course, the most important component of our atmosphere at all, and the number one greenhouse gas, the greenhouse gas that's more important than any greenhouse gas, water vapor. That might be a surprise to a lot of people, but water vapor is a greenhouse gas. So not all greenhouse gases are carbon-based. Try telling that one to a politician. So because we have this unique atmosphere, and why do we have this unique atmosphere? Plate tectonics. So the irony here is that we need volcanoes. Volcano eruptions are good for the Earth because volcanoes are the source of most of the carbon dioxide. So prior to humans putting carbon dioxide in the atmosphere, plants also do, or animals also put CO2 in the atmosphere. Volcanoes were the primary source of CO2. We need CO2 in the atmosphere. So currently the big debate is about how much CO2 is good and how much CO2 is bad. Like, oh my God, there's too much CO2 there, it's just going to melt. I hear that all the time, and currently our atmospheric concentration of carbon dioxide is somewhere around 400 parts per million, 400 ppm. Now in the past it's been much higher. In fact, during the Mesozoic, during the age of the dinosaurs, the atmospheric concentration of carbon dioxide was somewhere in the neighborhood of about 2,000 to 3,000 parts per million. When life really kicked off on Earth during the early part of the Paleozoic, 450 million years ago, atmospheric concentrations of carbon dioxide were 6,000 parts per million. So anybody who ever tells you that CO2 concentration is increasing above 400 parts per million is going to have catastrophic impacts on the Earth, they don't have the whole picture. If we really want to stop CO2 emissions, and we want to stop atmospheric concentrations of CO2 from increasing, we need to stop cutting down trees. And we're doing this globally. We're doing this everywhere. And the irony about the deforestation is most of the deforestation is occurring on government-regulated or government-owned land. Right here in the United States, every year, the United States Forest Service leases to foreign countries, foreign corporations, thousands and thousands of acres of forested land in Oregon and Washington. And those companies come in, those countries, they completely deforest the land. They cut every piece of lumber they can get out of that. So our own government is aiding and abetting in climate change. And climate change is occurring because of humans cutting down trees and creating deserts. And we'll talk about that a little more in detail. So this is why our Earth is unique. Active plate tectonics. So we need earthquakes. We need places to move around. We need convection. This is what helps keep the Earth alive. Mars had this. Mars actually had an active plate tectonic system. There's a fault on Mars that mimics the San Andreas fault. It's much larger than the San Andreas fault. And so there's good evidence that at one time Mars had an active tectonic system, but because Mars is a smaller planet, it cooled, its crust got too thick, plates couldn't move anymore, volcanoes couldn't erupt anymore, and the planet basically died. So what's inside the Earth? Well, there's liquid, a semi-liquid material consisting of silica and oxygen. So 45% of what's inside the Earth, that magma that's floating around, is silica and oxygen. Now when you put silica and oxygen together, you get SiO2, which is quartz, or in generic terms, it's glass. So basically we're kind of a glass ball. Other important elements are aluminum, iron, magnesium, calcium, potassium, sulfur, and sodium. So these are kind of all essential for life. And all the above elements are the basic building blocks for minerals and rocks. So most rocks consist of silica and oxygen. All igneous rocks, rocks that come out of volcanoes, rocks that form under the ground as magma, all igneous rocks contain silica and oxygen. A lot of sedimentary rocks also contain silica and oxygen. Some contain calcium carbonate, like limestones and those sort of rocks. A lot of rocks contain minerals that contain magnesium, calcium, and potassium. So here's a diagram showing the Earth's crust versus the whole Earth. So notice that the whole Earth, if you took the crust and the liquid, melted everything, remelted it, we basically consist of basically three essential elements: iron, oxygen, and silica. As it turns out, these three things, iron, these elements, oxygen, and silica, are the main components in basaltic rock. Basaltic rock is that black rock that comes out of volcanoes. We call it lava. We call it magma when it's under the ground. When it comes to the surface, we call it lava. As that lava cools and solidifies, it turns into a black rock we call basalt. You can see this really prominently in Hawaii. This is what makes up the ocean basins of the world. Magnesium is also found in those rocks. So these are very heavy elements. And then there's some nickel, some sulfur, calcium, aluminum, and others that is basically gold, silver, all the precious metals, copper. And then the Earth's crust is which is where we live, a little bit different, largely oxygen and silica. And then there's a fair amount of aluminum, iron, magnesium, calcium, potassium, and sodium. And so the Earth mostly consists of silica, oxygen, iron, and magnesium. So the lithosphere, the crust. So lithosphere is a Greek word that simply means crust. So the surface of the Earth is named lithosphere, excuse me, due to the temperature difference from the interior of the Earth to the surface of the Earth is obviously cooler. Otherwise we won't be able to walk on it. The deeper you go in the crust, the closer you get towards the magmatic rock, the liquid rock, the hotter it gets. Miners discovered this. There's a mine in South Africa, a gold mine. That mine is so deep that they actually have cool boxes. They have little refrigerated areas where the miners have to go in and cool off because the temperatures are so high down there. They have to pump in air. They have to pump in refrigeration in these mines. And so because of the fact that there's a difference in temperature, this is why you find different elements. So at the surface here, we find things like aluminum, calcium, potassium. These are low temperature elements. They can't exist inside the Earth in a solid state. They would be liquid. So the reason we find these different elements on the surface of the Earth is all due to a temperature differential. So now understand that. All right, plate tectonics. The crust of the Earth is made up of plates. These plates move at slow rates, centimeters per year over geological time. It's because of the plate movements, when the plates converge, when they come together, they create mountains, either in the form of volcanoes, or when continents crunch together, they'll uplift crust, forming a large mountain range. A good example of that is the Himalayas. Currently, India is crashing its way into China, and is creating a mountain range between the two countries we call the Himalayas. This is uplifted rock due to two plates converging, coming together. In other places, plates subduct and they go underneath the plate. That plate melts, comes up as magma, and forms volcanoes. Those volcanoes then spew that magma onto the surface, which is then we call lava. And a good example of that is the Pacific Northwest, Northern California, Oregon, and Washington, where Mount St. Helens, Mount Rainier are formed because of that process. So oceans consist of iron and basaltic-rich rock, lava. They're dark in color. When we talk about igneous rocks later on, we're going to refer to these rocks as mafic. Mafic means magnesium iron. It's another one of those Greek terms. And then rocks that make up continents tend to be lighter in color and lighter in weight, which is why continents are at the high spots of the Earth's surface. Oceans are at the low spots because oceans are rich in iron, magnesium, very dense, very heavy metals, and that's why the ocean basins, the basalt, that's why the oceans are there, that's why the water occupied those regions, is because they are topographically lower due to density. So continents consist of light color rock, which are generally quartz-rich, silica and oxygen, white, tan, pink, and red are the colors of those rocks. So plate tectonics keeps the Earth alive through the addition of greenhouse gases, carbon dioxide. Volcanic gases are rich in water vapor, and water vapor is the most important greenhouse gas. So volcanoes can modify climate by making it warmer or making it cooler. So volcanoes can do two things. They can make climate either warmer or can make it cooler. They make it cooler by dumping tons of volcanic ash into the atmosphere. That ash has silica and oxygen, quartz, which is basically glass. That glass has a tendency to reflect incoming solar radiation. That results in a cooler Earth. After the ash settles out, the atmospheric concentrations of carbon dioxide increase because of volcanic activity, and it's a CO2 because of the structure of the carbon to oxygen molecule, that molecule actually acts like an insulator and actually retains the heat of Earth. So the reason that the Earth's surface is warm and the atmosphere is warm is because of greenhouse gases and the greenhouse effect. And we'll talk about it later on. We'll talk about global warming. So Alfred Wegener, 1915, proposed the hypothesis that the continents were once together. He used 4 lines of evidence for that. He used the fit of the continents. He goes, they fit together like a puzzle. He saw that there was matching geology from continent to continent, that the rocks and the mountain ranges matched if you slid those continents back together. He looked at things like paleoclimates, where deserts naturally occur. So deserts generally occur at 30 degrees north and south latitude. Wegener saw that. He said, well, wait a minute, these deserts are way out of place. So these continents have moved. Coal deposits form in very tropical environments. And yet we find coal deposits today in very northern latitudes. So Wegener recognized that those places at one time were closer to the equator when they formed. So he used the whole thing to fit together, matching fossils, matching geology, and climates. So these are the 4 lines of evidence. He basically produced a treatise, The Origins of Continents and Oceans. He presented to the Academy of Sciences in 1915, and his hypothesis was rejected. And part of the reason why it was rejected is that Wegener went against conventional thinking of the time. He really did. He basically took everything that scientists believed at the time and turned it upside down. He completely did things different. This was nothing new. All throughout history, any time a scientist came up with a new idea, they were chastised. They were ostracized. It's amazing what's occurred, and it seems to repeat itself in history. At one time, we believed that the Earth was the center of the universe and that everything revolved around us, including the sun. When astronomers came up and said that's not correct, that the sun is the center of the universe, they were ostracized. And a lot of it was because of political religion beliefs that God created the earth was the center of the universe, and when scientists go against teachings, biblical teachings, they're immediately challenged, and they were, especially in those days. So Wegener, in part, I think there was a lot of bad politics of the day, and his hypothesis was rejected, in large part probably due to politics. So he had this idea of Pangea. Pangea then breaks apart and forms the continents today. So certainly continental drift was an idea far before its time. He had these 4 main points: the fit of the continents, so know those. Fossil evidence from the Mesozoic era, so he looked at fossils that were 250 million years old. These are the first part of the Mesozoic. These are the early reptilian dinosaur fossils that he looked at. Matching rock types and structures, similarities across continents. And then paleoclimate. He found deserts that are out of place. He found glaciers that left scour marks into rock, and when you slide South America and Africa back together, those scour marks match those striations made by glaciers. So those are his 4 lines of evidence. This is basically showing the similarities of rocks between Africa and North America. The Appalachian Mountains have a counterpart in Africa, and so do the rocks. So Wegener recognized that. He recognized that there were glaciers that existed. Glaciers don't go across oceans. So when this glacier existed, it left the gouge marks, the scours, the striations in South America. And in Africa, those continents were together when those glaciers formed. Today we know that India used to be down here. India is literally the poster child when it comes to plate tectonics. India went from the southern hemisphere all the way to the northern hemisphere. It's amazing how far India went. And so India is now crunching its way against China and creating the Himalayan mountain ranges, the tallest mountains in the world right now, on Earth, I should say. And so Wegener recognized these aspects, that these continents were together when these glaciers existed. So because of plate tectonics, we know, and because of rocks, we know what the Earth looked like throughout its history. This is what the southwestern United States looked like at a time called the Cambrian. This is when life really started to explode on Earth. In fact, it's often referred to as the Cambrian Explosion. This light blue area here, which is where Nevada and western Arizona, most all of Utah, and of course California didn't even exist at that time. California is going to exist because there's a bunch of continents way over here, and Australia and Antarctica are going to break off and they're going to glue themselves onto the North American continent. So 510 million years ago, there was no California basically. There was no landmass that we could call California. Nevada and Utah were basically very shallow continental shelves, and this is a great place for life to flourish. So we find a lot of fossils in these regions, trilobites that lived during the Cambrian, and this kind of helped kick off the Cambrian explosion. At that time, this also was a tropical area. So we know the North American continent was further south than it is today, closer to the equator. In fact, it was right practically on the equator. And then this is what it looked like during the Devonian. So actually, as we got younger, the oceans transgressed even further inland. And throughout the Devonian, this is when the rocks of the Grand Canyon are going to be formed. So the rocks of the Grand Canyon formed throughout the Cambrian, all the way through the Paleozoic, so the Cambrian, the Ordovician, the Silurian, the Devonian, throughout the Pennsylvanian, the Mississippian, into the Permian. And so shallow seas basically deposit a rock called limestone. Tectonics is later going to come along. Microplates are going to start adding themselves onto the North American continent. We're going to see collision between these plates. And all this is going to uplift. And then when it uplifts, the oceans are going to recede. There's going to be so much uplift that the Grand Canyon, the rocks in the Grand Canyon were formed below sea level, are going to rise far above sea level to 6,000 feet. And then the Colorado River is going to cut down through it, exposing those sediments. This is what the southwest United States looked like during the Mesozoic. So still, California is just beginning to form now. Gondwana land is breaking up. Pieces of Australia, pieces of Antarctica are on a plate like a conveyor belt, and they are starting to attach themselves onto the western United States. So the land that makes up the Baja Peninsula, all the way up through Southern California, Northern California, all the way up into Oregon, Washington, British Columbia, even into Alaska, was a series of microcontinents that collided with the North American continent. So plate tectonics helps explain this. They're able to identify rocks and fossils. All of these pieces of evidence helps us reconstruct what the Earth was like during the Mesozoic and 510 million years ago during the Paleozoic. So the great debate, objections to continental drift hypothesis, was simply that Wegener could not explain how the plates moved. And this was kind of the downfall of his whole treatise and his whole hypothesis, is that when he was asked, he said, so Alfred, and I could just see how it probably went on that day. I mean, I could just see the ridicule that was going on in the background. That, you know, so Alfred, so how do these continents move? And he said, well, maybe they kind of broke through the ocean's crust, much like icebreakers cut through ice, and they drifted. And he was laughed at. His entire hypothesis was rejected. And when he made that statement, he was kind of correct. Because we are floating. We're floating on magma. So the continents do move. They do float like glaciers, but on magma. There was strong opposition from all areas of the scientific community. So basically, Alfred Wegener went against the grain. And this has certainly been a paradigm throughout the history. So continental drift, the scientific method, Wegener's hypothesis was correct in principle. It did contain some incorrect details, and he did not have the ability in 1915 to map the bottom of the ocean. That's going to come later, when the United States Navy comes along and starts mapping the ocean floor, and they're going to discover paleomagnetism. They're going to discover seafloor spreading, and that the Earth consists of plates. So, were there other aspects? Definitely, Wegener, yeah. He was a threat to conventional science thinking at the time, and he was a threat. Because everything that those scientists were saying back in 1915, they were wrong. They told the United States Navy that the deepest part of the Atlantic Ocean was in the center. When the United States Navy built submarines and launched them, those submarines crashed into the mountain range in the middle Atlantic Ocean that wasn't supposed to be there. So the scientists were wrong. So in 1915, Wegener proposed his hypothesis. They thought that the oceans were the oldest features on Earth, that the oceans were flat, the deepest part of the ocean in the center, 180 degrees from what we know today. And he basically said that basically the continents were old, and it was thought that the continents were young by scientists in 1915. And throughout history, several scientists have proposed new explanations, and every time they have just come under scrutiny. And so do we see this today? I mean, look at our current president of the United States. Now, I'm not saying that I'm for or against. I'm just saying that Donald Trump has a different way of doing things than most politicians. So he is non-conventional. You know, he came in and deregulated the economy. He got rid of a lot of laws, streamlined a lot of process to build the economy. And that's kind of the way he does things. That's just his way. That's not the way of a lot of Congress people. A lot of senators don't like that. And so he's coming under a lot of scrutiny here. You know, so we have a philosophy of the Americans, which is quite different from the Republicans. So we have two political parties in this country. And in general, if you're a Republican, you have beliefs, and you have completely different beliefs if you're a Democrat. I'm not saying either one's right or wrong. I'm just saying that they're different. And it actually is good to have two different parties because it creates a dialogue as long as we learn to be civil about things. I have friends that are on both sides of the equations, and I love talking with them about things because I like to hear both sides, and then I can come up with my own conclusions after I've heard both sides. So I'm not endorsing President Trump. I'm simply relating the past to what's going on today. Another person that came up with a new concept that was heavily disputed was basically Darwin. So when Darwin talked about the origin of the species and evolution, immediately when he said that word evolution, no, you can't talk about that. But what Darwin, his entire life was about the species of animals, the evolution of animals and plants. In his latter part of his chapters, he made the critical error statement of the time, and that was, he said, well, if other animal species have evolved over time, then perhaps humans too. Well, as soon as he said that, he went against the clergy. He went against religion, because in the Bible it says we were created as we are, in the likeness of God. And for a scientist to come along and say, well, maybe we're a lesser organism that evolved over time to where we are today, that simply went against everything. So we have to be careful right now, because I watch all the networks and there is a lot of misleading information out there. My advice to you, research, analyze, and come up with your own conclusion. Don't let somebody else make up your mind for you. Okay, so what Wegener did not know, that was later discovered, is that within the interior of the Earth there's magma that circulates. We call this convection. So we need to know this word, convection. Convection is important. Convection, convection, convection. Convection is what drives plate tectonics. It's because of magma circulating. Some of that magma that circulates makes it to the surface. We call that volcanoes. This magma, this convection, is what drives plate tectonics. This is what drives plate tectonics. This adds new crust in the middle of the ocean, called the Mid-Atlantic Ridge. It pushes that crust aside. Other areas, old crust is being subducted underneath continents. It's melting. It's returning. So nature recycles, constantly working to recycle everything. So nature builds mountains, goes through weathering, breaks those components down into smaller particles, then erosion can take place to move that material elsewhere, redeposit as a new rock. That new rock can then weather out into new sediments, and the whole process just goes and goes and goes. So convection. Inside the Earth, there's our inner core. It's iron. This magma is circulating around this inner core. It creates an electromagnetic field. Because of this magma circulating, it helps these plates move. So here is basically showing how convection works. Hot material will rise to the surface. It's lighter, it's less dense. As that hot material rises to the surface, it then cools, becomes more dense, and it sinks. So you get this circulation of hot to cool. Warms up again, rises. That's what convection is. And so we have these convection cells all around Earth. These convection cells are magma, which is very rich in iron. That iron-rich material goes around the iron core, creates an electromagnetic field, and also creates magnetism. So basically, magnetism and electricity are very similar. They're not identical, but they're very similar. So what happens is that in one spot of the Earth that's weak, this material comes up and it creates a ridge. It then spews out hot iron-rich rock. As that iron-rich rock cools, it compresses, it'll form depressions. So you start out with an upwelling, then it forms a rift valley. That rift valley cools and then fills up with water. And as new crust is added, the ocean grows over time. And this is what basically is how the Atlantic Ocean grew. So we realize that this is what Earth looked like when Pangea was together. When Africa, South America, Europe, everybody's together, magma starts its way to the surface through a break in the Earth's crust. It forms a rift valley. So here's Africa, and here's South America, or here's North America and Europe. They're separating. Then this stuff becomes cooler, fills them with water. As the Atlantic Ocean opened up, it pushed Europe to the east, it pushed North America to the west. In over 250 million years, the Atlantic Ocean opened up into what we see today. So this is the basic for plate tectonics. So continental drift is what Wegener came up with. Plate tectonics is what we call it today. So we took Wegener's 4 ideas, we then combined them with 3 ideas, and we now have a new working hypothesis theory called plate tectonics. And that plate tectonics was, or is, the rebirth of Wegener's 1915 hypothesis. So one of the things that really is important in this is that I keep telling you about this iron and this magma. Well, that iron, as it turns out, iron molecules point towards magnetic poles. So you can go to a store and buy a compass. When I was a Boy Scout, I had to buy a compass. Essential thing when you go on hikes, you have to have your compass. And so the compass has basically a piece of iron-rich metal in it that points towards the North Pole. And as it turns out, when this hot magma comes to the surface and it cools, before it cools, the iron molecules point towards the North Pole. And that is a process we call paleomagnetism. So within volcanic rocks, there are iron molecules that point themselves towards the magnetic North Pole. So magnetized minerals show the direction of the Earth's magnetism poles, and it basically provides what their latitude is. So, here, we'll use a lightsaber. Let the force be with you. So, this is an iron molecule. It's hot, it's in liquid lava. As that lava cools and solidifies, this iron molecule is going to point itself towards the North Pole. Not only will it point itself towards the North Pole, it'll actually dip like this. So when it gets towards the North Pole, it's dipping like this. When it's at the equator, it's like this. So between the equator, which is at 0, 10 degrees, 20 degrees, 30, 40, 50, so forth, degrees north latitude, we can find out where the rocks were actually formed, at what latitude, because of the way that the iron molecules are tilted. There was one problem though. When Rear Admiral Hess took samples of the ocean floor, all the iron molecules didn't match up. Some of them pointed 180 degrees in the wrong direction. This was puzzling. What the heck is going on here? How can this be? So the scientific revolution began. Rear Admiral Hess of the United States Navy was given just literally a boatload of money and a bunch of boats and some submarines to go out and study the bottom of the ocean. The Navy was really ticked off with the scientists. They said, hey, you guys told us that the Atlantic Ocean was flat, featureless, and that the deepest part of the Atlantic Ocean was in the middle. Guess what's in the middle of the Atlantic Ocean? A mountain range. I'll explain that one. They couldn't. So the United States Navy took control. They became the scientists. They had a vested interest because they wanted to secure the United States military by putting nuclear warheads on submarines, because if the Russians discovered where our submarine was, we could simply move it. And so Hess discovered that at that mid-Atlantic ridge, new crust was being added to the Earth. And that new crust, when it came in, it pushed the old crust aside. This is a process called seafloor spraying. And then he saw that these iron molecules, some were pointing north and some were pointing south. So it'd be like this. Over here in these rocks, we have iron molecules that are pointing north. Okay? Go over here and look at these rocks over here. These iron molecules are pointing south. And then you find some where they were pointing north again, and then south again. So he found that along the ocean, there were these different iron molecules pointing in different directions, south versus north. And the result was, say, who nobody to have a duel with, you know? So the result was that they realized that the Earth's magnetism switched. So Earth's magnetic North Pole and Earth's magnetic South Pole, on an average of every 200,000 years, these poles switch. That doesn't mean that geography changes, that the South Pole becomes the North Pole and vice versa. It simply means that magnetism switches. What would happen if magnetism switched today? We probably won't even notice it. Birds would get screwed up because it is believed that birds migrate based on magnetism. Our GPS systems would be messed up, so you'd be going southbound on the 405 freeway. Your GPS would tell you you're going north. We have to kind of reverse things in order to fit the magnetic reversal. We are overdue for a magnetic reversal. We think it's occurring now. A lot of speculation on when it's going to switch again. But we know that every 200,000 years that the Earth's magnetism switches. So Hess discovers this in volcanic rock in the ocean floor. And then there were two guys, California guys actually, in 1963, Vine and Matthews. They were actually working on rocks out in California. This is out near Mammoth, in the valleys east of the Sierra Nevada mountains, and they discovered the same thing. They were drilling into these volcanic rocks, and the deeper they went, suddenly there was a reversal in magnetism. So this is a good example where Hess discovers this independently, and then Vine and Matthews rediscovered the same process in volcanic rocks in California. So this is where science, when it's pure and it's true, we can really come up with some really cool ideas. So this is what it looks like. As the new crust is being added, as those iron molecules are now in a liquid state, they orientate themselves towards the North Pole. That rock cools. That magnetic signature is recorded in the crust. And when you look at the ocean, we see a flipping of these North-South Pole orientations. And this occurs on average every 200,000 years. We are long overdue for a magnetic reversal. Right now, NOVA has a really good piece on about geomagnetic reversals. and they say it's beginning to occur right now, that we're seeing opposite magnetic anomalies in the northern hemisphere and in the southern hemisphere. And this is in magma. They think that the magnetic poles are beginning to switch. Some speculate it's going to take years for it to happen. Other scientists speculate it's going to occur overnight. So we'll see when it happens. So scientific revolution, geometric reversals, the Earth's magnetic field periodically reverses polarity. The north magnetism becomes the south, and the south becomes the north. So it's just magnetism that switches, and not the poles themselves. The Earth doesn't go upside down. It's purely magnetism. When we looked at these molecules, these iron molecules in this volcanic rock, so the iron molecules are going to point themselves towards the North Pole. So here's my iron molecule, so I'm pointing towards north right now. That way is north. So my iron molecule is pointing towards the North Pole. And it also tells the latitude by the tilt. So if it's at the equator, it's going to be like this. 10 degrees north, latitude 20, 30, 40, so forth. When they looked at this magnetism in rock, it appeared as if the North Pole had moved. Not just switched, but it appeared like it had moved. And this is the key word. The apparent movement of the magnetic poles illustrated in magnetized rocks indicates that the continents have moved. So the poles did not move. The poles pretty much remained stationary. North Pole and South Pole, they varied a little bit magnetically, but they don't go like, you're not going to find the North Pole at the equator and the South Pole at the other end of the equator. They're pretty much staying where they are because of the geophysical parameters of the Earth, because of the mass, because of the spinning. The electromagnetic field is occurring in that direction. So the North Pole and the South Poles are always going to be at the top and the bottom of the Earth. But the North Pole seemed to have moved when you look at magnetized rocks. And this baffled scientists. Well, how can that be? And then they talk about, well, remember Wagner talked about the swamps producing coal? And yet we find coal in northern Europe and North America? Maybe those continents were further south. So when they actually push the continents back together again, reform Pangea, the polar wandering curves matched. So basically the poles did not move, the continents did. So this geometric reversals, paleomagnetism, was the most convincing evidence set forth to support the concept of continental drift. So the most convincing evidence of all was this whole concept of magnetism. And magnetism is really an important attribute to science right now. Magnetism and electricity are really close cousins. They're interrelated in a lot of geophysical ways and a lot of physical ways. Their curves are a little bit different, but other than that, it's pretty close. And so magnetism is essentially electricity. Electricity creates electromagnetic fields. And so paleomagnetism. And it's all because, why? Because we have this iron core. And we have an Earth that consists of a lot of this stuff, iron. Lots of iron. And it's because of this iron-rich rock circulating with convection around that core that creates the electromagnetic field. So continental drift and paleomagnetism, the polar wandering was a second line of evidence. The curves for North America and Europe have different but similar paths. They were separated by 24 degrees latitude, and how you could get rid of that 24 degrees of latitude. So here, this basically shows when you plot, look at magnetized rocks, this is where the North Pole was 100 million years ago, according to the North American plate, and this is where it was in the Eurasian plate. This is where it was 200 million years ago, North American, Eurasian, 300 million years ago, North American plate, Eurasian plate, and so forth. When you slide the plates back together again and reform Pangea, the curves match up pretty good. Now the further back we go, the harder it is to reconstruct things because some of the rock record is lost due to erosion and the recycling of material. So this plate tectonics is a new paradigm. We now know that the Earth consists of major plates. Each one of these plates is moving. And we name these plates according to the continents that they are on. So we have the South American plate, which is where South America is. We have the African plate. Guess what continent's there? Africa. And so forth. And we know that this lithosphere that we live on, this very thin crust. So think of the Earth as an uncooked egg. The shell, the white shell, is where we live. Underneath us is the liquid stuff, the gooey stuff. And so this new paradigm, they discovered plates. So in the 1960s, there were three major discoveries. Paleomagnetism, seafloor spreading. So paleomagnetism was probably the most important. Seafloor spreading and plates. And this basically gave Wegener's ideas. So we use his four ideas plus the United States Navy's ideas and people like Vine and Matthews to come up with a new theory called plate tectonics. So we know today that the Earth consists of all these plates, and it's the plate boundaries where you find earthquakes and volcanoes. So both earthquakes and volcanoes are associated with plate boundaries. So here in our part of the world, California, we are right on the boundary between the North America plate, which is moving to the west, against the Pacific plate, which is kind of really turning. The Pacific plate is turning in a counterclockwise direction. And because we're on the boundary of two plates in California, between the Pacific plate and the North America plate, because of that, we have the San Andreas Fault. So our San Andreas Fault is a result of a plate boundary between two plates that are moving in different directions. So the Pacific plate in California is moving more to the north and west, more to the north, where the North American plate is moving to the west. So here in this area, these plates are moving side by side, creating the San Andreas Fault. And we'll talk about the San Andreas Fault in a lot more detail. So this is a new paradigm. So what is a paradigm? It's a general consensus and a way of thought. And so remember, scientists in the 1960s discovered these new ideas. The scientists in 1915, when Wegener proposed this hypothesis, their paradigms were 180 degrees from what we think today. So this is the evolution of science, and science is an evolving field. It's not static. So this plate tectonics, this new paradigm, plate boundaries. There are different types of plate boundaries. And I'm going to conclude this lecture here and then pick up with the second half where I talk about the plate boundaries. So that way you don't have to watch the entire video, which gets long. Plus, I need a break. I need to get some Scooby snacks. So I'll be back with the second half.